right, record. Okay, very glad to have Christina Vasilikopoulou talking about Hoplux Hopf algebras. So.
Great, thank you very much, John. It's a great pleasure. I'm very happy to be giving a talk in the Algebra Seminar of Masaryk University. So yeah, thanks to the organizers for inviting me to this online thing. So today we'll be talking about Hoplux Hopf algebras. So this was and is a joint project with Joost Verkroijse, Mitchell Buckley, and Timmy Fierman. So this was my team back in 2017 when I was a postdoc in Brussels, ULB, the university there. And we worked on this project since then and the continuation of this project. And only recently this thing got accepted to a journal, so it will appear very shortly in Higher Structures. So I will briefly just go over the main points of this work. And of course, you can go on the archive and see all the details, the things I'm not going to say today about these Hoplux Hopf algebras. So let me give you the outline of my talk today. I will start with some preliminaries, and that will include bimonoids in ordinary monoidal categories and Hopf monoids there, as well as there are many object generalizations, namely Hopf categories and semi-Hopf categories and Hopf categories. So this is our starting point for our talk today. The new thing that we did is that we introduced some new notions of a generalization of bimonoids and Hopf monoids, but in the two categorical context. So this will be the definitions of Hoplux bimonoids and Hoplux Hopf monoids, but in the context of a monoidal bicategory now, rather than in a monoidal ordinary category. And then what we're going to do is we're going to go over concretely the description of a specific symmetric monoidal bicategory of interest. It has this notation here, span V. We will give its descriptions. And why do we care about this bicategory? Because for us, the basic goal of this work, as was sketched in the abstract for the talk, was to actually be able to express Hopf categories, this many object generalization in a sense, specifically as a Hopf type object in some bicategory. And that's exactly the case for the notion of a Hoplux Hopf algebra in span V. Okay, so all these definitions will build up to our final result of expressing Hopf categories as Hoplux Hopf monoids in this specific bicategory. That's a lot of words, I understand, but let's go through the definitions and hopefully it will be clear what's going on here. Okay, so let's start with the bimonoids in braided monoidal categories. So we fix this braided monoidal category here, V. And let me just briefly recall the definition of a bimonoid. So in any monoidal category, we can have monoids and we can have comonoids. These are objects that come together with multiplication and unit for the monoid and co-multiplication and co-unit for the comonoid. And these are associative and unital. Okay, so the ordinary definition of a monoid, but in a context of a monoidal category. Now for a bimonoid, we ask for an object to have both these structures, both a monoid and a comonoid structure, but they need to be compatible in a specific sense. And the compatibility is expressed via these four commutative diagrams here. Okay, so you can see that, for example, in the first commutative diagram, we have the interaction of multiplication and co-multiplication, and then we have all the different combinations. We have unit and co-multiplication, multiplication and co-unit, and so on. So this is the definition of a bimonoid. Another equivalent way of expressing what a bimonoid is to think that when V is braided, so that's actually important, and I will come back to that in a later slide, then both the categories of monoids and comonoids are monoidal. They inherit the monoidal structure from V. So these commutative diagrams here express that, for example, the multiplication is a comonoid morphism. Okay, so we basically take a monoid in the category of comonoids, or dually or symmetrically in a sense, a comonoid in the category of monoids. So these four diagrams do exactly that. This is the one line definition of what a monoid is, or sorry, a bimonoid is. Okay, so then what is a bimonoid morphism? It's the reasonable thing. You ask for a morphism between the two things that preserves the multiplication in unit and co-multiplication and co-unit in the usual sense. In that if you first do multiplication and then do your map, then this is the same as doing twice your map and then the multiplication in the other monoid. So the usual definition of a monoid map and a comonoid map give you the usual bimonoid morphism. So we have a category of bimonoids and bimonoid morphisms in any braided monoidal category. Great. Then we go on to a Hopf monoid, and a Hopf monoid is a bimonoid with some extra stuff. And the extra stuff, which is actually a property, not a structure, because it's unique when it exists, it's an antipode. So what is an antipode? It's an endo arrow on my carrier object here, M, that satisfies these two commutativities, the top and the bottom commutativity of this shape here. So again, there's a one-line definition of what an antipode is in a sense, not just by writing this, this commutative diagram, which might not mean much to a lot of people. And the idea is the following. In any monoidal category, V, so I'm fixing V here, and if you take the home sets here, where the first entry is a comonoid and the second entry is a monoid, so this is a more general result of what I'm using here, you can actually find this convolution monoidal structure on this category here. And what is convolution? For example, in our case, then if you take two of these endomaps from M to M, then you can first co-multiply and then go to M times M and then take their tensor and then use the multiplication of M to go back to M. So this is the tensor product, the convolution tensor product for this endo-home set of our monoidal category. And the unit object is not, as somebody would just guess on the top of their head, the identity map on M. Instead, it's just this. So you first go via the co-unit to I, and then by the unit to M. And why am I saying all this? Because, in fact, an antipode is an inverse of the identity on M under this structure. And you can see that already. You see the top is basically delta, then 1 times S, which is what's going on here in the middle, and then multiplications. And this is the convolution of S and 1M. And in the middle line, I have the identity, the unit in my monoidal category. So the top and the bottom just say that S is the two-sided inverse, the left and the right-hand side inverse of the identity map in this monoidal category here under convolution. Okay, great. So we can actually show that every bimonoid morphism preserve antipodes. So we in fact have a full subcategory of Hopf monoids inside bimonoids for any braided monoidal category V. Great, so this is very famous in classical algebra. Hopf algebras are all around. Their representations are very important. People have been studying them for decades. So this is just the category theory of it in a braided monoidal category, not just in vector spaces or R modules as was the classical setting. Great. So what happened around 2016 or a bit earlier than that, but that's when it was published, is that Battista Vercroise, my collaborator, and Canapil published this this article called Hopf categories. And as I said in the beginning, Hopf categories are basically the many object generalization of what we just talked about. But in which sense? Let me just make this precise. Everybody knows that a nice way of thinking of a monoid is a one object category. So in that sense, we can think of categories as being monoids with many objects in a sense. So the same idea was followed here. We want to generalize Hopf monoids in that direction. Okay, there could be, you could generalize into any direction you want. For Hopf categories, you want to have the same idea with the many objects like we have for categories and monoids in our structure. So let us see how the definition goes there. And for the definition, let me just write down what I said earlier in brief, in passing, that when you have a braiding in V, and only then, you can actually have a monoidal structure in comonoids. And let me just sketch this. When you have two comonoids, C and D, and you envision some comonoid structure on this tensor product, then of course you only have delta and delta to go down to this. But if you don't have a switch map to go between them, then there's no other natural way to go from C times D to the tensor product of this object by itself, which is C times D times C times D. So you need the braiding for that. So having said that, when you have a braided monoidal category V, comonoids are monoidal, therefore you can enrich in them. We can enrich in any monoidal category, and in particular, we can enrich in comonoids. So the first definition here, which is that of a semi-Hopf V category, this is a mouthful, is actually sheerly just saying a comonoid enriched category. So again, this is the one-line definition. Let me break it down in smaller pieces. What's going on here is that, first of all, you basically have an enriched category. Every comonoid is, first of all, an object in V. So what we have here is an enriched composition, and I'm writing things with indices because they're a bit more handy when you write a lot of those indices down. So you have x, y, and y, z goes to x, z, and this is a global multiplication in the sense that that the indices are not fixed. They vary over things that agree on the middle thing. This is basically when the domain of the first arrow and the codomain of the other match, but in the enriched setting, written as arrows in V. But then we have the fact that this is an enriched category in comonoids. So all these home objects are not just mere objects in V, they are comonoids. So they better come with a local, in the sense of home categories, local co-multiplication. So for every fixed 2 indices now, they don't vary as before. For every fixed 2, you have this co-multiplication arrow and this co-unit arrow. And of course, we have a bunch of axioms that express that these are all co-algebras and these are all enriched categories. But because we marry them together, asking for this to be a comonoid enriched category, they also need to have some compatibility. For example, these maps need to be comonoid maps. They need to be co-algebra maps because of this comonoid enriched category. And that's how we get this generalization, because remember when we were talking about bimonoids, we had something like this, okay? We had this compatibility of multiplication and co-multiplication. But now that we inflated this into a many object setting, what we will have here is a bunch of indices and a bunch of maps that respect those indices. So the new axiom, well, the axiom of a semi-Hopf category here has this form. So it's exactly of the same shape as before, only now I need to take care of the indices. And mu goes from varied indices and delta goes for fixed indices. And of course, this is the same for the other 3 axioms. I didn't have space here to fit them all. But I hope you got the idea of how to generalize from the one object case to the many object case, at least here. Let me just say that, well, a semi-Hopf category might sound a bit strange name here, but another option would be, if you want to go from a bimonoid to a category, you would ask for this to be a bicategory. But of course, no one wants that. A bicategory is a very well-established structure, and you don't want to call something else like that. So that's why semi-Hopf arose. But this is basically the generalization of a bimonoid in the many object settings. So that's great. And what is a Hopf category? It's precisely what we had before, but now we have this antipode-like structure. Again, we have the indices, we have this many object situation, and they flip, they're switched from hxy to hyx, and then they need to satisfy 2 axioms. And again, before we had this axiom, say the top of the thing I had before, and if we want to put indices in the game, and that's what we have here, again, this blows up in a sense, and we have this co-multiplication, which is local, multiplication, which is global, and this is the one of the 2 commutativities. There's another one with slightly different indices, but again, I just hope you got the picture, and going through every axiom in detail is not the topic of the talk anyway. So that is the idea of Hopf categories. These are the definition at least. And with comonoid enriched functors, we have those 2 categories. So the semi-Hopf categories are just comonoid enriched categories and functors. So it's not, it's just a different name for a very well-established thing. But then Hopf categories are those things that come with this antipode in that sense. And let me just briefly go through some examples. And the first thing that we should make sure is that this satisfies its role, its goal of being this many object generalization, and it is true, and you already kind of saw it. If you fix a one object thing here, well, all the x and y's are the same, they disappear, and they give you the previous diagrams we saw. So indeed, a one object semi-Hopf category is a bimonoid, and a one object Hopf category is a Hopf monoid in V, in the one object case. Great. Then let us think about some more elaborate examples. Then suppose you have a category which is Cartesian monoidal. So the monoidal structure comes from the categorical products. Then we know that every object in V has a canonical comonoid structure that comes from the diagonals and the unique object down to the, sorry, the unique arrow down to the singleton, to the terminal object. So in that case, asking for a category to be enriched in comonoids because of this isomorphism here, it's redundant. You don't get anything new. So in fact, any V category is semi-Hopf. Asking for a comonoid enriched category is the same as a V category. So no new structure here if V is Cartesian monoidal. Okay. Another more interesting example that what was the result of a completely different project that was during my PhD thesis, and it just happened that it fell under this situation, is that so during my PhD thesis I was looking into Swidler's so-called universal measuring coalgebras, and they, in the generalized setting, actually induced an enrichment of algebras and coalgebras, those objects, those universal measuring objects. So in fact, having some extra structure on V, some extra assumptions on V, which is that of a monoidal closed category, and also local presentability, because it makes adjoint theorem so nice to work with, we can actually say safely that the monoids are actually a semi-Hopf V category. So that's nice, two completely different things coming together. And another example that I think shed some light on these Hopf categories is the fact that every Hopf ordinary category, so just enriching over set, is a groupoid. So let's think about this for a second. Set is a Cartesian, taken as a Cartesian monoidal category. We already know that any semi-Hopf category is just a category. You don't get any new structure. But now what you have on top of it is the antipodes. And with the antipodes here, if you think about this, these are home sets now. So for every arrow from X to Y, this is giving you some arrow from Y to X. It smells like an inverse, but you don't know that it's an inverse yet. But when you write down those two axioms that we had for invertibility, for the antipode, that's exactly what we get. That the antipode, in fact, for every arrow from X to Y, give you the inverse from Y to X. So a Hopf set category is a groupoid. So if we want to think about Hopf V categories for an arbitrary category V, is really, something like a V groupoid. Sorry, someone trying to ask a question? No, sorry, I thought I heard something. Anyway, so yeah, these are the some examples here to make these notions, these new notions a little bit more grounded. So let us just dive in the new things. So this was already known when we started this project. We wanted to, as I said, understand Hopf categories as a Hopf type object in a two categorical setting. So that was the main goal. It was to actually introduce these notions that relax the monoid comonoid compatibility in a two categorical setting. And of course, this is a very usual theme in two category theory in higher categories. When you have some strict commutativity, for example, of diagrams that give you some axioms in the ordinary setting, then going to the two categorical setting, you have this flexibility, this luxury of asking of any two cell going inside this previously commutative square. So basically that's what's going to happen here. And hopefully the definitions will just be this relaxation of the previous bimonoid idea in a straightforward sense. So now we're fixing a braided monoidal bicategory. So this is the usual setting, usual for the people that have seen this before, but let me just briefly say that now the tensor product is a pseudo functor of categories, okay? And then you have the braiding, which is a bunch of pseudo-natural equivalences between the things you would expect. So it's the natural generalization of a monoidal category in the bicategorical setting. And then we have the well-established notions of a pseudo-monoid and a pseudo-comonoid, okay? And these are like before, there are objects with multiplications and units, and the co-multiplications and co-units. But now in the earlier associativity square, when you had three objects and you were multiplying in your the two different ways you can multiply to go down to one object, then this is not equal anymore, it is isomorphic. So there is an isomorphism, a structure isomorphism in there. And of course, whenever we insert an isomorphism instead of an equality, we're going to have a bunch of axioms then, talking about what happens when you multiply four things and so on and so forth. So pseudomonoid and pseudocomonoid are already there for any braided monoidal bicategory. If you want to think about this a little bit more grounded, you can think about a pseudomonoid in cat, which is a monoidal category, when you have the tensor product being associative only up to iso, not strictly equal. And then those things can have lax or oplax maps. And again, this has to do with the fact that instead of asking for your map to strictly preserve multiplications, you ask for it to laxly preserve them or oplax preserve them. And again, the idea behind this is you can think about it if you want as lax monoidal functors or oplax monoidal functors. They're all special cases of these things, and the axioms are very similar looking. So now what happens is that we want to define what an oplax bimonoid is. And an oplax bimonoid for us and for our purposes, and you will see hopefully why we needed this definition, is first of all a pseudomonoid and a pseudocomonoid as before, but now in the two categorical setting. But now we need some compatibility that is not expressed anymore as strict equalities, but instead you insert these two cells, okay? So you have this theta, you have theta 0, chi 0, the same diagrams as before, but now you have the structure to cells. And again, now we're going to have a bunch of axioms that come with those structure to cells. So these are the satisfying axioms. They are in the appendix of our paper. They are long, but again, we don't have to just think about them, make them out of our heads, but instead we can think about them in a very formal and nice way. So what's going on really here is the following. We have, for any monoidal bicategory, for every braided monoidal category, we have the categories of pseudomonoids. Okay, so these objects here form a pseudomonoid, and you can choose them to have Oplax maps. You can do that. And then again, this is monoidal when K is braided, and then I can take a pseudocomonoid in there. And if you think about this, this is what I wrote. So writing a pseudocomonoid inside a pseudomonoid, a category of pseudomonoids, will give me all these four two cells here. These are Oplax maps that express that the co-multiplication, the co-unit are Oplax maps or of pseudomonoids. I know there's a lot of words there, but this is the formal definition of this category, the category of Oplax bimonoids. Well, the bicategory, we're in the bicategory K, and we can choose to take this with Oplax maps if we want. And yes, so this is the definition of this structure of Oplax bimonoids and Oplax bimonoid maps between them. Great. So like before, inserting those two cells and adding those axioms. And let me, before go to the Oplax Hopf monoid, which is the counterpart for the Hopf monoid in this higher structure, let me discuss this a little bit. So in the classical setting, one of the very important things about bimonoids, and it's actually a characterization of them in a Tanaka way of thinking, is that whenever you have an ordinary bimonoid in a monoidal category, then the category of modules, so if you think of the bimonoid just as a monoid and take the modules of this monoid, have a monoidal structure, and this forgetful functor that forgets the actions and everything else is strict monoidal. Okay, and as I said, this actually characterizes bimonoids among monoids. So whenever you have this, whenever you have a monoidal structure here, which is essentially the same as the one in V, then it is enough for you to reconstruct the rest of the bimonoid structure that was missing. So that's an important part of bimonoid theory, and we wanted to see, and of course every good notion, when you introduce it, you want it to look as nice as it can. So in fact, we wanted to do something similar for Oplax bimonoids, and of course for that, we're not going to use modules, we're going to use Oplax modules, okay? So an Oplax module for a pseudomonoid M has an action as would an ordinary module, but now instead of again having a strict commutativity here between the usual things you would expect, the action followed by the action, or the multiplication of the monoid followed by the action, then you have this two cell that say they laxly relate to one another, or Oplaxly in this sense. Depends on what convention you use, of course. So we have the category of Oplax F modules, of course, a bunch of axioms, which we don't write down. And then the result here reads that if you have an Oplax bimonoid, then the bicategory, bicategories here, have a monoidal structure. And then the forgetful functor down to K is strict monoidal. So you can mimic the classical setting here and say that there is a monoidal structure on the Oplax M modules with Oplax maps, for example, and this is precisely the same as the monoidal structure in K. Let me just show you this structure very briefly. I'm not going to go into details. So the deal here is that you start with an M module X and an M module Y, and we want to show that the object X tensor Y has an M module structure. So for this to have an M module structure, you need an action of this form. So you need to start from this and go down to X times Y. And for this, you use the co-multiplication and then the braiding and then the two actions of the two modules here. But that's not enough, because we need this Xi and this Xi0. And of course, we're going to form them as big two-cell composites here. So let me just show the shape of this. So for Xi of this new M module here, I'm going to have a bunch of squares here and isomorphisms between them, basically using theta, which comes from the fact that M is an Oplax bimonoid. So theta was my first two-cell in the previous slide, expressing the Oplax compatibility of multiplication and co-multiplication, and Xi, which is the earlier, the structure two cell for the two M modules X and Y. And similarly for the unit two cell here, I'm going to use theta 0 again from M being an Oplax bimonoid, and Xi0, which comes from both those M modules being Oplax. So this is just a very brief sketch of how this would go. Great. Okay, so I'm just saying a few results here as I go. So let us go to the notion of an Oplax-Hopf monoid. In the same spirit as for a Hopf monoid, you expect this to be an Oplax bimonoid with something extra, with this antipode that we had before. But again, we're going to relax this antipode in a specific sense. So how are we going to relax the antipode? Well, the axiom at the very end of the bottom of this page will be very similar to what we had before, with two cells between this. But let me motivate this concept, because it's actually something very natural that arises from something abstract. So first of all, there is a notion of an Oplax inverse for X in a monoidal V. So remember, earlier we had this inverse in a monoidal category when you have, which is equal to the identity, but now I'm asking for an Oplax inverse in a monoidal category V, which is another object where taking X times Y is not equal to Y, but actually there is a map between X times Y and Y times X to I. And having these two maps, I'm asking also that there are two equations here satisfied, and they have to do with taking the tensors of these two maps with a switched order, in a sense, with one and on the other side. And they need to be equal, and also these maps need to be isomorphic. This looks a little bit strange when you first look at it, but in fact, this is a special case of a so-called firm Morita context in any bicategory. So this notion, let me just digress very quickly here, was introduced by L. Kautitz around 2008, if I'm not mistaken. And this Morita context in a bicategory as a name, when you write it down in a bicategory and you apply to the bicategory of algebras, bimodules, and bimodule maps, gives you the usual notion of a Morita context. So that's where it came from. And the only thing we did new here is we added this firmness here that, again, in the context of bimodules, give you something that is related to firm bimodules. So that's why the firm was added here. And the firmness just says, on top of just a Morita context, that these maps are isomorphic, isomorphism, sorry. So all I'm saying is that this is a more general notion as a one object case for a monoidal category V. And the only thing that was new, in a sense, is that we asked for something stricter in our case, because that was our example at hand. It required of this extra thing, the firmness, in fact. Okay, so this is a special case of something more general. We can leave it there. And the idea here is that we define an Oplax antipode for an Oplax bimonoid to be precisely an Oplax inverse of 1M inside this endo-home category with convolution like before. So it's the same statement as before. The difference is this Oplax thing here and the fact that K is not a monoidal category, it's a monoidal bicategory. But it was known from back in the day, or found in writings of Day and Street, that for any braided monoidal bicategory here, if the first guy is a pseudo-comonoid and the second guy is a pseudomonoid, then you can do the same thing as before, write the same convolution maps as before, and prove that this thing is also monoidal category. So we're asking here for something to be an Oplax inverse of 1M, very similar to the classical setting, but now grown to this bicategorical setting. But if I want to write it down, as I promised at the beginning, this is the usual definition with two cells inserted in between, not having strict equalities, but having these two cells here writing then. And of course, we have these two axioms here that come from these two weird things at the beginning, and all these cells need to be isomorphisms. So this is the definition of an Oplax antipode for an Oplax bimonoid. And of course, our definition of an Oplax-Hopf monoid is that of a bimonoid with that extra thing on top. And we can also have a bicategory of Oplax-Hopf monoids and the appropriate notion of morphisms between them. And these two bicategories, the Hopf monoids, Oplax-Hopf monoids, and Oplax bimonoids, are the key players in what happens in this work. Okay, but before I go on and take the examples of these new notions in this monoidal bicategory I promised earlier, this span V, which we need to first describe, let us see some easier example first, which will be necessary for what comes later. So let's first work in a much easier braided monoidal bicategory, symmetric monoidal bicategory, which is span. So we take the bicategory span of sets, spans, and span maps between them. We take the monoidal structure of the Cartesian product of sets and the terminal object there, and we want to look at a specifically an object of the form x squared in this bicategory. So the first point here is that for reasons that are clear, and I will explain in a second, that every set, in fact, has a strict monoid structure in span. So we said earlier that in any Cartesian monoidal category, you have this unique comonoid structure coming from the diagonal and the unique map down to the terminal. But now I'm not in sets, I am in span. And span is not Cartesian anymore. The Cartesian product of sets is not anymore the categorical product in span, which is a disjoint union. So all I'm saying here is that we're using this comonoid structure from set and we map it down to span, and the span maps here are of this form. So for x squared, I have this span as the co-multiplication and this span as the co-unit. And you see the right-hand side is precisely what I was talking about earlier, this diagonal and terminal, the unique map down to the terminal, but on the left-hand side, I have identities. And that's very typical. When we go from set to span, there's a very natural way of doing that. There is a very nice functor there that takes every function and maps it to the span, where one of the two legs is the identity and the other is the morphism. So this is a natural construction coming from set, but now I want to view this in span, and actually this has a comonoid structure. We can actually write down the axioms. Before I go to the next structure, let me just say that I say a strict comonoid structure, not a pseudo-comonoid structure, because this came from a strict comonoid structure and said, you can actually write down the axioms, and this will be co-associative strictly. There will be no isomorphism there. There will be the identity. So this is a special case of a pseudo-comonoid, basically, okay? Just by thinking that pullbacks along identities are identities. That's where it boils down to. Anyway, let's go to the other structure of interest. Remember, I'm trying to build an Oplax-Hopf monoid. So for that, I need a pseudo-comonoid structure, a pseudo-monoid structure, an Oplax bimonoid structure on top of these two, and then an Oplax antipode to finish up. So now I'm trying to give the pseudo-monoid structure, and let me elaborate on this for a little bit. For every set, we can build a co-discrete category, x squared. What do I mean by this? Take the objects of x as the objects of your category, and then for every pair of objects x and y, you are allowed to only have one map. So that's why this is a co-discrete category. So in fact, morphisms in this category are precisely x squared. Writing a map from x to y is writing the pair x, y. There's only one. And this is a groupoid because you have the inverse of xy is yx, and the only identity map is just going from x to x. So that's why this is a groupoid. Well, the multiplication in this groupoid, well, the composition in this category basically says that if you have x and y, the pair x and y, which is your map from x to y, and a map from y to z, then you can actually compose to give a map from x to z. So you're kind of throwing away the middle index. So this is the idea, this is the mentality behind this pseudo-monoid structure in span. So if we look on the left, we have x to the power 4 and x to the power 2, and on top we have x cubed. So this is like having the composable morphisms in a sense, having what? Having x and y and z. So the left span leg says duplicate the middle guy, having x, y, y, z, and the right leg says throw away the middle guy, having just x, z. So this map here basically is the multiplication in this groupoid, the composition in this groupoid, starting from x, y, and y, z, and then going down to x, z. And on the right-hand side, I also have the identities of this groupoid. So this is just an idea behind the pseudo-monoid structure. We can show that this multiplication and with this unit, there are isomorphisms, associativity isomorphisms and unit isomorphisms, and all the axioms work and everything is fine. So we choose, it's up to us to choose what comonoid and pseudo-monoid structure we want. We choose these two, which is comonoid and pseudo-monoid here. So then with those chosen comonoid and pseudo-monoid structures, we can actually build up a unique Oplax bimonoid on x squared. I'm not going to write it down again due to space and time, but you can find it in the paper if you're interested. So we found this theta, theta 0, chi, chi 0, two cells. Remember, we are in span, so all these things are span maps, in fact. So we found these 4 span maps, and they satisfy the Oplax bimonoid axioms using those monoid and pseudo-monoid structure. And on top of that, we can say that x squared is an Oplax Hopf monoid. And what is the Oplax antipode? Well, it's basically just the switch map on the right and the identity on the left. Okay, so with these structures, the ones I showed you and the ones I didn't show you, X squared is an Hoppolax Hopf monoid in span. So that's one non-trivial example of an Hoppolax Hopf monoid in a bicategory. And let me just very briefly comment on this unique part here. So I said it's unique because span is a very particular it's a very nice bicategory. Many people like working in this setting. And one of the things that happens in span is that if you have a span map between two spans and the target span has one of the two legs being a monic morphism, then this map is unique. It's not unique, sorry. There is at most one map between them using the monomorphism property. So if you find one span map, then you're good. There's no other. That's it. So that's why this uniqueness arises in this step. And let me just finish up this slide by saying span is a very symmetric it's a self-dual category in a sense. So you can take any span and reverse it and see what happens there. There's an isomorphism there in a sense. So what I'm trying to say here is that if we take all these structures and we reverse the spans, here I'm going to have a monoid structure. Here I'm going to have a pseudo-comonoid structure. Here I'm going to get another Hoppolax antipode, and I still get an Hoppolax Hopf. That you will see right now. So what are the zero cells of this bicategory? For the moment, I'm not asking for any structure on V. It can be any category. Doesn't have to be monoidal. So the zero cells will be pairs of a set, so the object in span, along with a functor from X viewed as a discrete category down to V. X viewed as a discrete category means that there are no maps there, so I can actually just view this functor as a collection of objects in V, indexed by elements in X, okay? So this is a zero cell, a set, and basically an X collection, an X index collection of objects in V, which is this M guy. Now, what is a one cell between two things of this sort? As we said, first of all, we're going to start from the structure in span. So we're asking for a span between the underlying sets of those functors. But then we're also asking for a natural transformation between this shape here. And if you look at the shape here, the left-hand side is all just sets and functions. So again, this being a natural transformation doesn't say much. This just says that I have a bunch of components. I have a bunch of morphisms in V. There are no naturality squares because there are no morphisms, no non-identity morphisms in S. So this is essentially the extra V structure associated to this span between the two sets. It's great. These things compose, they use the pullbacks as we do in span. So this composition is associative up to isomorphism because it uses pullbacks. And then the two cells are maps of spans, first of all. So we have the target span and the domain span and a map that makes the two triangle commutes. And now we don't have extra things happening in V, rather we have a factorization property. So we're asking for the two things, this alpha and beta from before, these two natural transformations, to satisfy this property. That's basically say, if you take the components in V on elements that came from U, they need to be the same as alpha. So this is a very nice factorization property, it's not extra structure. And yes, this is a bicategory. And moreover, when V is monoidal, we can actually endow this bicategory with a monoidal structure. And this is basically the component-wise monoidal structure saying you take two things here and you take the tensor product of mx and ny inside V. So that's why I said the point-wise, just take the tensor product in V of those two things. Let me say here to be very clear that there is a more general construction than what I just described, a more abstract and a little harder to describe, that was introduced by Gabriele Bohm maybe 2 or 3 years back. For an arbitrary monoidal bicategory K. And what we did here for our purposes is we took a monoidal 1 category and we viewed it with trivial 2 cells. And that's how we build up this bicategory here, this monoidal bicategory that comes from this more general construction from span K. In fact, it's interesting that Bohm introduced this bicategory for similar purposes to ours. We were in contact at the time. because she also wanted to express Hopf categories as Hopf monads. And she did express Hopf categories as specific sorts of Hopf monads in here for a specific K, but we wanted to do something else. We didn't want to separate the monoid and the comonoid structure. We wanted to view them both over the same monoidal structure. And that's what we're doing here. We're trying to revive the symmetry between the monoid and the comonoid structure for Hopf categories, because they look very different, but in this context, they're over the same monoidal structure, which we thought was very interesting and exciting. Okay, so this is the monoidal bicategory span V. It looks a bit strange. We said that it comes down from a completely different, completely more abstract construction there. So let me say a couple things about this bicategory. First of all, as you could maybe already see, a lot of things going in span V is actually happening in span. And one way of saying this is that there's a strict monoidal functor of bicategories that just forgets all data associated to V. So you had your set and your functor, you forget your functor. You had your span and your natural informations, you forget your natural information. And you had a map of spans with a property anyway, so you just forget the property. And that's this functor. It's a strict functor of bicategories in the sense that the composition is the same, is taking pullbacks of spans. So it works in the same way. And also the monoidal structure is strictly mapped from the one to the other, because if I go back one thing, so here writing the monoidal structure of two functors here, the set on which this is upon is the Cartesian product of X and Y. So mapping down this thing to the underlying set is taking the Cartesian product of set, which is the monoidal structure in span, which is great. Okay. So this is a very important thing to begin with, that a lot of the structure going on in span V comes from span, but there is also an even nicer or more rich in a way that this functor comes in life. And the result here reads that if V has enough co-limits, specific co-limits, this forgetful functor is in fact a 2-op fibration, which I think is very, very interesting. So a 2-op fibration was, 2 fibrations were introduced by Mitchell Buckley, one of the team, some years back, and it was the 2 categorical generalization of the usual growth and deconstruction. So we followed those steps here, and we were able to recover span V via this modified growth and deconstruction. And the idea here is that you want to build a pseudo functor not down to cat, as would be your usual growth and deconstruction territory, but down to 2 cat, and then obtain a 2 category, a bicategory, depending on how good the pseudo functor is. In any case, what is the mapping here? Well, on objects, it gives you these functor categories, and of course, this is to be expected. These are the fibers in here, and we know that every object is something in a morphism functor, sorry, from X to V. So this is where all the objects in span V live, in those functor categories XV for a specified X. But then the interesting thing comes on the morphism side. So what happens on the arrows? Where do we map a span onto? We need to map it to a functor. And the functor is a very, very canonical thing to do, is the left can extension of precomposing with F along G. So starting with a span here, we can build this functor, and let me elaborate a little bit on this functor between these functor categories here. This says, start with a functor from X to V, then first precompose with F, go to S, and then take the left can extension of the top guy along G. And that gives you this arrow here. And if you think about this, this of course makes sense, because what we had earlier as a one cell in my category span V were certain natural transformations inside triangles like that, where here we had M and here we had N. Well, the universal property of the left can extension really tells you that you can view any 2-cell like this as factorizing, canonically through the left can extension. And that's the fibration, the ray-indexing idea going inside the 2 fibration here, 2-op fibration. Anyway, so yes, the 2-dimensional growth and deconstruction, then it can be proved that it is isomorphic to you. And I didn't say anything about 2 cells. You have to map the 2 cells somewhere and then take the modified 2-dimensional growth and deconstruction and show that this is isomorphic to you. Anyway, so all this is evidence that this span V is not, you know, an extraterrestrial thing. It's a very natural construction. It is very reasonable. And let me just come back to what I wanted to say from the top of this page. The fact that this functor is so nice, it's a strict monoidal, strict functor of bicategories, tells me that in particular, if I take any pseudomonoid, pseudocomonoid, Oplax bimonoid, or Oplax Hopf monoid in here, then via U, I map it to a same structure, same name structure down in span. And in fact, this was also part of the theory when we developed the theory for Hoplax bimonoids and Hoplax hop monoids. We showed that any braided monoidal pseudo-functor, which is the right level of generality at that level, preserves these Hoplax bimonoids and Hoplax hop monoids along monoidal bicategories. In any case, what's specifically interesting here is that whenever you're looking or you get in your hands an Hoplax hop monoid in span V, you should have in mind that there is an underlying Hoplax hop monoid in span. And it's no coincidence we spent a little time talking about X squared before, because in our case, for expressing hop categories as those objects in span V, we will use as the underlying set the X squared set with the earlier structure we defined, with the Hoplax hop monoid we defined. Okay, so it's part of the structure in a sense. X squared being an Hoplax hop monoid in span is part of the structure of Hoplax hop monoids in span V. You need to choose an underlying set with an Hoplax hop monoid structure if you are to go on. Okay, so we are ready to actually go into our final goal and just see the results briefly here. Hopf categories as Hoplax, Hopf algebras, which was the goal all along in the monoidal bicategory span V. So the idea that we followed is that every piece of structure of a Hopf category, all these global multiplications and local co-multiplications, correspond to specifically to some Hoplax Hopf monoid structure, to that of an Hoplax Hopf monoid structure in span V. So let us start from pseudomonoid, the pseudomonoid part. So the first result here is that a pseudomonoid in span V over X squared with the earlier groupoid pseudomonoid I was talking about is precisely a V category, the very well-known notion of a V category. So let me just very briefly show you the structure maps. Remember, a pseudomonoid in span V needs to come with multiplication and unit 1 cells, which in our case of span V, they are natural transformations going like this, okay? So this is the form of those things. This is a multiplication and this is a unit for an object in span V. And you see that on the left-hand side, I have the spans that were already predetermined for X squared with the structure I gave earlier. So this is the groupoid, multiplication, and this is the groupoid unit in a sense. So writing, asking for a multiplication of this sort, I can already write down the components of this natural transformation. Remember, these are just arrows in V, basically. They don't have any naturality condition. And writing down the components, I actually get precisely enriched composition and enriched and units of enriched categories just by writing down the components. And then asking, saying that this is a pseudomonoid means that there are distinguished isomorphisms. But remember, isomorphisms in this bicategory here, there are 2 cells and they come in 2 pieces in a sense. The first piece are maps of spans, and the map of spans were tackled when I decided and I proved in detail that X squared is a pseudomonoid along with a factorization property. Well, that factorization property gives me the 2 axioms of a V category. Okay, so I'm just sketching very in a hand-wavy way of how, starting from those things, you would get the V category axioms from the factorizations in span V, from the special form of 2 cells inside span V. Okay, so everything just falls into place. But this correspondence doesn't just sit on the level of objects. So we don't only have this for pseudomonoids, we also have this for pseudomonoid maps. So if you have 2 pseudomonoids of this form, X with underlying set X squared and G with underlying set Y squared, and you ask of this to be specifically of this form, and what do I mean specifically of this form? You again chose the span. You always are kind of predetermining the span. You're taking the fiber kind of over a specific span that you want to work with. And this span goes from the identity to F times F. And if we write down the components of alpha, if you think about this, the components of alpha go from HXY to G, FX, FY. And that's why F applies on the second step and not on the first step. And you get the usual form of a V functor that goes from HXY to G, FX, FY. In any case, I hope some of the things I say hand-wavily help some people, but feel free to ignore them and just see the written parts, which should give a clear picture of what's going on. So in fact, what we did here is that we can realize V cat as a specific subcategory of the pseudomonoid inside span V. Okay, so this is the first part of the first piece of the structure put in the specific part of the puzzle, in a sense. I'm not going to go into that detail for the rest of the structure. As I said, everything is in the paper, but let me just say that for the comonoid part, the strict comonoid we discussed, in fact, a comonoid in span V over the comonoid X squared is precisely a comonoid enriched graph. So now you don't have multiplications, enriched compositions or anything. You just have that everything, every object, every home object is locally a comonoid. And that's what you get from having a comonoid enriched graph. Okay, so that's the only structure you have there. Then an Hoplax bimonoid is a semi-Hopf category, and an Hoplax Hopf monoid is a Hopf category. So again, I'm not going into details there, but as if everything was predetermined, everything just falls into place, writing down all the respective structure cells, and it takes some time to write all these structure cells for Hoplax bimonoids and for Hoplax antipodes and everything, and writing down the factorizations always end up giving us the respective axioms that we need for a semi-Hopf category and a Hopf category. So at the end of the day, having similar correspondences for morphisms, they're all of the specific form as they were for V functors, having identity on top and F times F on the bottom for the span. We actually express Hopf VCAT as a subcategory of Hoplax Hopf monoids span V. And it's a very specific subcategory. It's a subcategory over objects of the form X squared and over morphisms of the form identity F times F. So it's a very well characterized subcategory that we care about. So indeed, a Hopf V category can be expressed as a Hoplax Hopf monoid in span V, and that is basically the end of the end of the talk. Let me see how much time I have. I have 2 minutes. Okay, so let me very briefly. So this was the goal. The goal was accomplished, but let me just say very briefly, just to get your curiosity going, that what happened in this work is that we were working through that, and then at the same time we realized that in the same setting, the same span V category, we were able to express something called Frobenius categories. It's not, there are other things called Frobenius categories. This is not one of them. So in the same underlying monoidal bicategory, by taking the well-known notion of a Frobenius pseudomonoid in there, we were able to define Frobenius V categories, and they have global multiplication like before, so they vary over things, but now they don't have a local co-multiplication, they have a global co-multiplication. And this is very interesting. Why? Because when you have a Frobenius and a Hopf monoid in a monoidal category, the multiplications and the co-multiplications look dual to each other. But then when you generalize in this setting, you see that they're not dual to each other anymore, because Frobenius categories have different kinds of co-multiplication, whereas Hopf categories have local co-multiplication things here. What I'm saying is that when you generalize, you're able to see better the differences between two classical notions like Hopf algebras and Frobenius algebras. And the topic of the next project we did, and is actually also just finished and will appear on Advances of Mathematics, is the fact that under which assumptions and under which constructions a Hopf V category is Frobenius. And this is there is a classical theory by Larson and Swidler that tells you when a Hopf algebra is a Frobenius algebra, under which conditions. So we generalize this for the many object versions of those two guys, Hopf algebras and Frobenius algebras. Anyway, I would stop there. Thank you very much for your attention. And these are some references if you want to have a look later.
John, you are muted.
Oh,
sorry. Silent round of applause for Christina. Yeah, thanks for the talk. And so if there are any questions, go ahead and ask a question. Feel free. Maybe I can ask a question. Is there, so this monoidal bicategory span over V, is that a double category?
Very good question, John. Well, span is definitely one. And now you attach all this V structure on this. I have never thought about this, but it could very possibly be one. Yeah, I haven't thought about this. That's a good question. Yeah, it could be.
I remember sometimes you can, like Mike Schulman had this stuff where you can, you know, do stuff with monoidal double categories. It's a bit more convenient than
Yes.
categories sometimes.
Right. I personally am all for this idea. I've been using this a lot through my research. So now you definitely put me through thoughts, because at some point Gabriella Baum and I were thinking about Hopf monads in double categories. And I'm thinking whether there is some relation there about all this. So yeah, this is something to look into. Thanks for that. Mm-hmm.
I have one more question that occurred to me. I know you said that in sets, a Hopf category is a groupoid.
Mm-hmm.
Is there some story that in any Cartesian category, is it so if you have a monoidal category in which the monoidal tensor product is the product, can you say what the Hopf categories are at that level of generality? Or
so yes, so in that I think I said it very briefly. I haven't really thought about this, but if there is a notion of a V groupoid, then that would be it in a sense. So if V is Cartesian, then if V is Cartesian, then you have an ordinary V category, and then you basically have some inversion maps between home objects. So you have H, XY, and HYX, and you have a map between them, and this satisfies an inverse-like property. So but you cannot talk about inverses anymore because you're in V, you're not in set. But I think people mention those things as V groupoids. So if you've seen V groupoids before, then fingers crossed they are Hopf V categories for Cartesian V. Mm-hmm.
I was just thinking that I was wondering what a Hopf cat category was. It seems like some weird thing where you have where the two cells are horizontally invertible, but
right, but not. Yes, that's interesting. Yeah, it looks like that. You can definitely invert. You can invert. You have a functor that inverts somehow your two cells in this vertical arrow, in this vertical direction. But yeah, I don't think so. In this original paper, I don't think they had many examples. I don't think they had this example. So yeah, it is something like that. I'm not sure about this. I can ask. I'm sure somebody has thought about this. I haven't seen it anywhere. Mm-hmm. Yep.
Any more questions?
I have a question and a comment. But firstly, thanks, Christina, for the talk. That was really, really interesting.
Thank you.
The comment was that, so I think the underlying category of span V, or at least if you take isomorphism classes of that, that rings a bell from a talk that Steve Lack actually gave to the Australian Category Seminar 2 days ago on Wednesday. Oh, yesterday, sorry, on Wednesday. And it looks like it's the, let me just say this very precisely. Yeah, so the strict category with byproducts over V. So I'm not sure whether it, yeah, so maybe if you pull up that
slides, I can find the slides, or I can ask Steve about that. Yeah, sure.
Yeah, just confirm with Steve that I haven't gotten something wrong, cross-checking my notes that I took that day with what you were saying today.
Okay.
But it did ring a bell to me. So the underlying category of span V.
That sounds good. I'm definitely going to have a look there. Thanks for that.
I think that was V being finite sets, if I recall correctly. Steve's talk.
Okay.
Okay. And a question I had was also whether there was a way to look at V natural transformations from this perspective as well, to get the whole of VCat.
As a two category. Yeah. So this is something that at the very end of this project, we didn't look into that because the paper was already something like 60 pages and we were very tired. But I definitely, at some point in my life, I definitely thought that that was the case. Yes, I had worked some preliminary things out, and I was pretty sure that was the case. And it's not so hard because, I mean, the structure is there. The two cells are there. I mean, formally they are there. You can write them down. Only we didn't. So the answer is yes, probably. 90% yes. Yes, then that's a good observation. Then we would get them as a two categorical structure. And all of these things would be something like a two categorical structure. Although, yes, I don't know what a natural transformation between Hopf categories is. But yes, for VCAT, I would expect this to be just straightforward. Yeah. Mm-hmm.
Let me quickly correct what I just said. So it wasn't that V was finite sets, but the spans were spans of finite sets.
Ah. Interesting.
Is there something about pointed sets? Finite pointed?
That was another part of that talk, but not for
were-
that particular construction that Adrian recalled.
Okay.
So for this talk, is there any connection between these Hopf categories and the quantum categories that have been studied by Day and Street?
At some point, so Joost, who's the older, and he also invented Hopf categories, he had mentioned how they are not the same, for sure.
Mm-hmm.
And that's why they chose a different name. So he was definitely aware of them, but I'm not aware of any relation, to be honest. I haven't looked very much into those. I know they exist, but I haven't really worked with them.
I know there's some sort of skewmanoidal viewpoint on those things, but
that's interesting.
Maybe that's not relevant here.
Yeah. No, but thanks for the pointer. Yeah. Right. Mm-hmm.
Okay, well, if there are no further questions, let's thank Christina again. Yeah,
Thank you.
And yeah, thanks very much for the talk. And so that's the end of it. And
thank you very much. Are there no tea, coffee, cookies? No, I'm kidding. Okay, thank you very much, and thanks for your patience, everyone.
Okay.
And thanks
for the talk.
Yeah,
See you soon.
Bye.
Bye.
Thank you.